All right, so in this lecture, we're going to go over section 2.8, and this is on the derivative as a function. So in the previous section, we started with a function, and we took this limit of this quotient, and it gave us a number, which we could associate to a function. And this was what we call the derivative of the function at a given point. And we could interpret this in lots of different ways. It could be interpreted as the rate of change of the function, or it could be interpreted as the slope of the tangent line. And now, in this section, we're just gonna, instead of thinking about the derivative as a number you associate to a function, we're gonna think about the derivative as a function itself. So that given a function, you can, in most cases, or at least in all the cases we're gonna look at, associate this thing called the derivative to it. And so it's gonna, in this derivative will be another function. All right, let me share my screen. Okay, so hopefully you can see what I'm seeing. So this is 2.8, the derivative as a function. So so in the last section we saw, so if I gave you a function and then a fixed number, oops, if I gave you a function f and a fixed number a, you could look at this limit of this ratio right here, the difference quotient. This right here is called the difference quotient, and then you can just give it a name called f prime of a. This is just notation to stand in for this complicated limit. And you write this if the limit exists, because the limit might not always exist. And we're going to see some examples where this limit exists. So if this limit exists, you use this notation to denote the limit. But now we're just going to think, instead of a being some fixed number, we're going to replace a by a variable f. And so now f prime is going to be a function. Is viewed as a function. And it's basically the same form. And so as I said, this is called the derivative of f. So f prime is viewed as a function. It's called the derivative of f. And the domain of it is going to be the set of all points x such that f prime exists. That is, such that this limit exists. So the domain of f prime is all of those x such that, let me just spell it out a little bit more, this limit exists. And if this limit exists, you call this f prime of x. So as it notes, this may be smaller than the domain of f. And again, we're going to see some examples where this is the case. In fact, it's possible, very possible that this set could be empty. There's no points for which the derivative exists. There's no points for which there are no points x for which this limit exists. It could be the empty set. In fact, let me pull up an example. I think it's the Weierstrass function. Yeah, so so here's an example of a function actually. It's a fractal. It has this fractal-like behavior. This is a function which is continuous. So it's continuous everywhere, but is differentiable nowhere. And so here's a plot of this curve. As it says, it has some fractal behavior right here. Oops. It has some fractal-like behavior. It has some self-similarity, meaning like if you zoom in on the curve at any point, it looks like the whole entire curve. So it has this self-similar behavior. And it's defined right here by this infinite series. We haven't talked about infinite series. This is something you'll look at in Calc 2. But this infinite series is basically like you're adding a bunch of infinitely many terms. And then A is between 1 and B is just any positive odd integer such that this inequality right here is true. And here is, I guess, an animation as you vary the parameter a. So a is again between 0 and 1 over here. And you can see as a varies between 1 and between 0.1 and 5, that can't be right. Innovation based on the increasing of the value a from 0.1 to 5. That doesn't make sense to me because a is supposed to be between 1 and 0 and 1. Anyways, but as this number increases, you can see it gets increasingly more craggy. And the idea is that it's going to be continuous because you can just draw this. In principle, you can draw this curve or this curve up here without lifting your pencil, but there are going to be corners. You can see that there are sharp corners appearing as the animation goes on. There are even corners in this picture right here. And these are going to be, when you have corners in your graph, when you have these sharp edges there, those are going to be points where you're not differentiable. But it turns out at every point X, you have a sharp corner. So it'll be continuous, but it won't be differentiable. But I've never seen the proof. I can't imagine that's actually easy to even give a proof in here, this document. No, they don't give a proof. So I imagine it's pretty tricky to prove that it is not differentiable. Anyways, there's a very bizarre function that is continuous everywhere, but not but differentiable nowhere. All right, so back to the text. So that would be the Weierstrass function would be an example where this set right here is empty. There are no points where the derivative exists. There are no points where this limit exists. And so one way, again, this is going back to something we already know, but one way of interpreting the derivative geometrically is as the slope of the tangent line to the graph at the point x, comma, f of x. So f prime of x gives you the slope of the tangent line passing through this point right here, x, comma, f of x. And that can actually be really useful when if you're given a shape of a graph. So here we're given this function, this is the shape, and we can actually get a rough idea of what the derivative looks like. So if you give a function from the real numbers to the real numbers, you can plot it, and the derivative will be a function from some set of real numbers to the real numbers. So you can plot the derivative as well. So we can graph a function, its derivative, its first derivative, and you can also take a second derivative. So you can plot the derivative of a function, and you can actually figure out a lot about what the graph of the function, the derivative looks like based off on the function, the graph of the function itself, the function you start with. So this graph right here is smooth. So continuous means basically that you can draw the graph without lifting the pen. And of course, there's that rigorous definition in terms of the limit. Differentiable means that not only is the graph, can you draw the graph without lifting the pencil, but it has to be done in a smooth fashion. So you can see that this graph is smooth. So differentiable roughly corresponds to the graph being smooth. And of course, there's a more rigorous formulation of being differentiable in terms of this limit right here existing. So again, we have this duality of intuition and rigor, and they should be like coexisting. So we have these intuitive ideas of what continuous differentiable should mean, and they should be grounded, or they should be based on some rigorous definition, and vice versa. There's just like interplay between intuition and rigor. So here's the original graph of the function reproduced down here. And so we want to know, what does the graph of the derivative look like? So to get that, we need to draw various tangent lines. So we have a tangent line here, tangent line here, tangent line here, here, and here. And again, remember the slope of the tangent line is going to be the value of the derivative. So the slope of this tangent line, they're saying that it's -1, so the derivative is -1 at that point. In fact, when you go up here, all these the slope of all these tangent lines are going to be negative, so that means the graph should be below the x-axis. And that's exactly what you have right here. So when you are so when you're at 0 and you going to the negative infinity, the graph is below the x-axis. See, the graph of the derivative, this is the graph of the derivative. It's below the x-axis. And then you have points, so it's 0 at this point B, so that means it should go through, the derivative should go through the x-axis, and it does. And then you have a point here at 1. This is a slope 1, so this point should be at height 1, and it is. And then we have another point where the slope is 0. And notice these from like, let's say point B to D right here, the slopes are positive, so the graph is going to be above the x-axis, and it is. So from B to D, the graph of the derivative is above the x-axis. But at D, point D here, where the slope is 0, that means it's got to pass through the x-axis again. And it does. And now from D to, like, I guess maybe this point right here, the slopes of the tangent lines are negative. So right here, for example, you have negative 2/3. So at this point, past D, going beyond D to positive infinity, the graph should be below the x-axis, and it is. So the derivative is negative. You see it's negative here. And then it starts to come up again. And maybe at some point here, maybe it'll cross through again. Who knows? It doesn't matter. So that's basically, so given, in other words, the graph of a function, you can get a rough idea of what the graph of the derivatives looks like by just drawing some tangent lines and determining whether or not the slope is positive, negative, or 0. And maybe you can actually work out, maybe like, for example, in this case, like this is approximately 2/3, this is 1, -1, this is 1. You won't know, in most cases, you won't know exactly what these slopes are unless you're given the function and you can take the derivative, but you can just say, oh yeah, like right here um, at A, the slope, the line is like angled down, so that has to have a negative slope. So it's got to be below the x-axis at A, and it is. So that's a qualitative way of working out the derivative. So here's an example too. So all the examples in here are more or less similar to the examples in the last section on 2.7. You're going to calculate the derivative in basically the exact same way. So I mean, we'll just quickly work through this because we've done calculations like this already. So we want to work out the derivative of, we want to find the formula of this f prime given that f of x is this. So we want to find out the derivative, and then I guess the domain maybe will be obvious. So this first equation right here is just by definition. This is by definition the derivative, this part right here. Okay. And now we plug in the function, specific function. So we have f so let's write down our functions we have. And so I have to keep scrolling up and down. I guess it's x cubed minus x. So we're going to evaluate this at x plus h, and then just at x. So that's why we have this x plus h cubed minus x plus h, and then put that in square brackets, and then minus just the original function itself. So if you compute this, you get, I guess it looks like this part here, x cubed plus 3x squared plus h plus 3x times h squared plus x, or sorry, h cubed. So if you FOIL that out, which is kind of tedious, but you get the thing I underlined, and then you have this negative right here. You distribute that through to get negative x, and then negative h. Okay, and then finally you have this negative right here, and you distribute that through to get negative x cubed and then plus x. So I'm kind of just skipping over some details and going actually writing down the arithmetic, because this is something we've already done. basically in the last section. Maybe not this exact example, but we've done things like this. So I'm just kind of want to go through this quickly though. And then this point now you just simplify the numerator and you notice there's a common factor. So to go from here to here, you just simplify the numerator and you notice there's a common factor of h everywhere. So you can divide that off. And then when you do that, you're left with 3x squared plus 3xh, h squared minus 1. And now this right here is this is continuous. Well, it's a polynomial. More specifically, it's a polynomial. It's a polynomial in H, so it implies continuous, right? This thing right here, this thing we're taking the limit of is continuous. So you could just plug in H is equal to 0. And when you do that, you get 3x squared minus 1. And this is another polynomial. So the derivative, in this case, the derivative of a polynomial is a polynomial. And so this is defined everywhere. So it's defined on all of the whole real line. All right, so here they give a graph. So this is the graph of the original function, x cubed minus h. And then, so this is x cubed minus h. And then we have the derivative is 3x squared minus 1. So let's first of all, before we like kind of compare these graphs, you can see that this is getting annoying doing these limit calculations. And in the next chapter, we're going to actually derive some rules for computing derivatives that are based on the limit definition. And remember, so let me just scroll up again. We have this limit definition here. Remember, this definition, there's a lot going on in this definition, more than you think at first. But remember that the limit is defined in terms of the epsilon and delta. So this has a ton of meaning packed into it. And so we're going to actually be able to derive a lot about the function from this definition here. So if you know a function is differentiable at a point, it's going to be very nice. It's going to have a lot of nice properties, and there are going to be a lot of nice rules for calculating derivatives. But they're all based on this limit definition, which itself is grounded in this epsilon delta definition. So there's a lot going on here. Of course, you don't have to remember all that, but just remember that there are a lot of details packed into this definition. So we're going to look at some rules so we can avoid having to compute derivatives by definition. In the same way that we derived a lot of rules for limits, so we could prove and calculate limits using nice rules rather than proving them using the epsilon delta definition which got tedious and cumbersome after a while. So that's, again, this is the whole project of mathematics is to like derive rules and consequences and techniques and tools from those basic fundamental definitions. So you can simplify your life a lot more. All right, so let's look at this graph again. So we see we have at this point right here, we have like, it looks like if you draw the tangent line, it's, well, I didn't draw it perfectly, right? But it looks like roughly it is horizontal. So this is going to be a 0 tangent line right here. So at this point, you should go through this x-axis, and it does. The derivative, I should say. And notice to the left of this point right here, if you draw tangent lines, they're very steep and they have positive slope, right? Very steep. So that's why we have this portion of the graph above the x-axis, because the slopes of the tangent line are positive. And then you come up to this point here, and it goes through the x-axis. And now the slopes of the tangent lines, let me get rid of some of this details because there's a lot. The slopes of the tangent lines are negative, right? This is a negative, this tangent line has a negative slope. And so that's why we have this portion of the graph right here below the x-axis, because those on that interval, basically, the slopes of the tangent lines are negative. Let me get rid of that. And then now you pass through here, and then here, at this point, again, you have another horizontal tangent line. So you're going to go through the x-axis, and you do see it right there. You go through the x-axis right there. And then you start having positive slopes again, right? Here's a positive slope. Not perfect, but let me just clean this up a little bit. So once you get to this point right here, now you start having positive slopes. So like here's a positive slope, and then here's like a positive slope. So again, now this portion of the graph should be above the pet. It should be above the x-axis. That's a tongue twister, and it is in fact above the x-axis. So um, do that sort of comparison when you're working through problems, so you can like really uh, tie all these ideas together, all these different perspectives on what a derivative is. All right, so here's an example we went through already, so I'll just be really brief. So we have this function, the square root of x here. We want to find the derivative and then state the domain. So here's going to be our first example where the domain of the derivative could be strictly smaller than the derivative of the domain of the derivative can be strictly smaller than the function, the domain of the function itself. The domain of f prime, though, will always be a subset of f. So let me actually write that on the side. So note, um, the domain, let's say the domain of f prime is always going to be a subset. Remember, this notation means subset. Let me make it a little cleaner, though. So this means subset, and then when you draw a line under it like that, that means it could be equal to. It's almost like, think about this as like less than or equal to, in a sense. It's the subset symbol is a lot like the less than or equal to. In fact, you can order sets using this subset. Like just with numbers, you have this less than or equal to relation. You can put a relation on the set of all sets, which is given by subset. And this gives you, so you can say that this set is less than this set, another set, if it's contained in it. Um, but for all I want to point out in this note is that the domain of the derivative is always a subset of the domain of the original function itself. Um, and then equality is possible. And then we'll say equality and strict inequality are both possible. So we already saw a case where equality is possible, right? Up here, when we took the derivative of a polynomial, this polynomial right here, x cubed minus x, we get this polynomial right here, and this is defined, so the domain of f is clearly just the whole real line, and because it's a polynomial, it's defined everywhere, and the derivative is all polynomial, so it's defined everywhere. So the domain is also equal to all of R. So you can have the domains are the same. In this example, though, they're not going to be the same. The domain of the derivative is going to be strictly contained in this, the domain of f. All right, so let's go through this really quickly, though. So this is just the definition of a derivative. Always write your definitions out before you solve the problem. It helps you memorize these definitions. And now, so we plug in x plus h into the square root, we get the square root of x plus h, and then we have minus f of x, which is square root of x. And we're going to do this rationalization trick. So we multiply and divide by the conjugate of the numerator. So we have to change this negative to this positive right here. And if you multiply, you got to divide, right? Otherwise, you're changing the fraction. So let me clean this up now. And when you distribute this numerator through to this numerator, when you FOIL it, you're gonna, the square roots go away, and you have x plus h minus x, and then in the denominator, just multiply the h by this denominator. Don't distribute it through, so just leave it like this right here. Just leave it like that. Just leave it as h times some nonsense. Okay, so let's get rid of that. And the numerator simplifies just to h. And now this h right here cancels with this h. And look at, so at this point, you have this thing that we're taking the limit of right here. it's a continuous function in H, and it's defined at H, right? I'm sorry, it's defined at 0. So just plug in the 0. Just plug in 0 for H, and you get this, which simplifies to this. And now note, this is not defined at 0. So this f prime of f exists if x is strictly bigger than 0. That is, this limit exists only if this f only if x is strictly bigger than 0. So the domain of f prime is all the positive numbers, while the domain of f is positive numbers, including 0 right here. And you can have 0. You can plug in 0 to the square root. So it's going to be, the domain is going to be slightly smaller than the domain of f. All right, so here's another, again, a comparison. I'm going to leave it up to you to, well, maybe this one is actually interesting to go through. Let's see. So here's the graph of f of x, which is x squared, and here's the graph of the derivative. So what do they say? When x is close to 0, square root of x is also close to 0. Oh yeah, so the derivative should be very large. Because remember, in other words, if x is a small number, square root of x is going to be also small. So when you take 1 over that and then times the 2, there's with the 2 in the grand scheme of things, that's going to be really big. So that makes sense that this should be going off to infinity like it does here. As you get closer to the origin, and that makes sense. Why? Because like look at tangent lines. If you look at tangent lines near the origin, so like this, if you start here, it's pretty steep, but then you go here, it's steeper, and then as you get really close to the origin, like these tangent lines are getting steeper and steeper and steeper. In other words, these tangent lines are, you could say, approaching a vertical line, right? And which has infinite slope. So that makes sense that your derivative should be, in a sense, infinite, or at least go off to infinity like it does here. So these tangent lines right here, they're getting steeper and steeper and steeper. They're approaching a vertical line which has infinite slope, right? Vertical lines have infinite slope. So it makes sense that if your derivative, which describes the slope, it makes sense that your derivative should go off to infinity when you get closer and closer to 0. And that's exactly what happens here. And then when you get further away from 0 over here, when you start going out over this way, you can see the slopes start to like flatten out. And that's exactly what you're seeing here. The function is, and in fact, they're getting the slopes right here are getting closer to a vertical line, or sorry, horizontal line. So when you approach um, 0, your tangent lines are getting more and more vertical, so they're going to infinity. But when you go away from 0, you can see that the lines are becoming flatter and flatter, becoming more horizontal, so they're approaching 0, and that's exactly what we're seeing here. That the graph of the derivative is approaching a 0. So note, let me put this on the side. So note, as you approach, let's use some notation. So as x goes to 0, let's use some notation. Let's be mathematicians and use notation to simplify our discussion. So as x approaches 0 from the right, tangent lines are approaching a vertical line. Oops. Vertical line. So that means that the derivative should be kind of going off to infinity as x approaches 0 from the right. And that's exactly what it does. We see that here. And you can also just take the limit of this derivative right here and see that it goes off to infinity. And then as x as x goes off to infinity, i.e., let's say, so now as x, on the other hand, um, as x goes off to infinity, i.e. away from zero, going further and further from zero, we can see that the tangent lines, tangents, that is, the tangent lines are becoming more and more horizontal. So what that means, and horizontal means zero slope. So that means that the derivative f prime of x should be going towards zero. And that's exactly what you see over here. So it's good to analyze these problems from many different perspectives because you'll have this holistic approach to these problems, and it'll just be able to help you solve problems faster, but also help you to identify maybe errors you're making. If you can, like, because sometimes when you're doing all this, like say this complicated arithmetic right here, when you do all this complicated arithmetic right here, you can be lost in the details sometimes. So when you do all this, sometimes you can like lose sight of what you're even trying to do when you do all this nonsense right here. So it's always good to have these pictures in your head so you can like compare the two. You can compare, and this is really the duality, the interplay of algebra and geometry. So you want to always keep those two things in the back of your head. Ultimately, everything is justified through this nonsense right here. That is through the algebra. That you do the formal manipulation of the symbols to justify everything. But it's always good to have these pictures right here and these pictures right here and this intuition right here in the back of your head. So you can compare the geometry compare the pictures and your intuition here with the algebra. It kind of like breathes life into the algebra in a sense. This is all really sterile right here. It's kind of boring. It gets annoying actually to do this kind of calculation right here. But once you can see that it has has a lot of geometric meaning, it gets more interesting. All right, so here's another example. I'm not going to bother going through this. I'll let you go through this if you want. And of course, if you have any questions on this example, if a step doesn't make sense, feel free to reach out to me. We can try to resolve it over email, or we can set up a Zoom meeting. All right, so sometimes it's helpful to have different notation to denote the same thing. So here's just a little section on some different notation. So we've been looking at f prime. Now if you just let y equal to f of x, sometimes it's helpful to just denote the derivative by y prime. So like y is some function of x, and so y is changing with respect to x, so you can talk about the derivative of y. Here's some really nice notation right here. This is called the Leibniz notation. And if you remember, uh, Leibniz was one of the founders of calculus along with Newton. So Newton was in England, Leibniz was in Germany, and they were sort of developing calculus independently of each other. I don't even think they knew of each other, actually. I don't think they ever wrote, maybe they wrote letters together. I don't know. They definitely did develop calculus independently, though. So there's this notation right here, dy dx or df dx. If you don't want to use y, you just want to use the original function itself. Um, this is nice notation here too, because we're going to think about the derivative as an operator. So remember, the limit was like this, we called it some sort of operator, right? And it's going to turn out that the derivative has some nice operator properties. Here's some more notation. I don't think I've used that really much at all. So as I said, we're gonna deduce some rules for derivatives, and it's going to turn out that there are a lot of nice rules that are analogous to the limit ones. So using this dy dx, it turns out that, for example, if you want to take the derivative of a sum of two functions with a scalar multiple here, so c is a constant. So let me write up here, c, some real nine, it's a constant, so it's real number constant. And you want to take the derivative of this linear, this right here is called a linear combination of f and g. So this is called the linear, oops, this is called a linear combination of f and g, if you want to compute the derivative of this linear combination, um, it's simply you what this is equal to is you can factor out, you can like pull out the scalar, this real number, take the derivative of f of x, and then add the derivative of g of x. So the derivative, in a sense, distributes over sums and scalar multiples. So maybe over here, what this says right here is that d over dx is a linear operator on the space of functions, or some subset of the space of functions, because not every function is going to be differentiable. Not even every continuous function is going to be differentiable. So, and the fact that it's this rule right here, going here to here, basically just follows from the fact that it's true for limits. You know that limits distribute over linear combinations of f and g. So the fact that's gonna like you can like bootstrap that in a sense to derivatives as well. So it's just more notation. All right, so we've talked about differentiability at a point, but it turns out so what that means, so a function is differentiable at a just means that f prime of a exists, which we've already mentioned already. And then you can talk about differentiability on an open interval or open set. So like a comma b, or a to infinity, or negative infinity a, or just the whole real line. Maybe you're differentiable on the whole real line. So you're differentiable on such an interval if you're differentiable at every number. Same thing with continuity. Remember, if you're continuous set on a set, it just means you're continuous at every point in the set. If you're differentiable on a set, it just means you're differentiable at every point in the set. All right, so here's going to be an interesting function to kind of illustrate the difference between continuous and differentiable. So the question is this differentiable? And the answer is gonna be sort of, because it depends upon it. So we're asking, is this differentiable? I guess what we're asking, the question's actually kind of vague. So we're taking um f to be a function from R to R, and it's given by the absolute value of x. And so what we're asking, is this differentiable? And the answer is no. There's going to be a problem. There's going to be issue with one, or sorry, zero. It's not going to be differentiable at zero. Of course, if you restrict the domain to this, so you can now consider f as a function from negative infinity to zero, and then from zero to infinity to the r. So here is no. If you instead consider on this domain, the answer is yes. So you have to be kind of careful what you mean um, when you ask, is the function differentiable? It depends upon the domain. So we're just gonna take the domain to be the whole real line, and the answer is gonna be no. So here's how to see this. Well, first of all, let's just look at the graph. I don't know if they give the graph. So here's the graph. Yeah, remember this is the graph of oops of the absolute value function. And the problem where it's not going to be zero, it's going to be except that zero. Where it's not going to be differentiable is zero. And intuitively, that's because it has a kink at this point, right? Intuitively, the reason why is that if you like consider points here and points here, like a point over here, not sure why it's not drawing. No, this kid is freezing. Okay, let's give this a second. Anyway, so the reason why it's not going to be differentiable at zero is because if you consider tangent lines on the left and then on the right, and getting closer and closer to zero, but not at zero, the tangent lines on the left of zero are going to have a slope of -1, whereas the tangent lines on the right are going to have a slope of +1. So if you take the left and the right hand limits, they're not going to be the same. You're going to get different numbers. So that's roughly why kinks like this correspond to points where you're not differentiable. Because if you consider tangent lines on the left or the right of that kink, you're going to get different numbers. One number will be positive, one number will be negative, depending on the type of kink. And you get that if you, let's see, I used this GeoGebra here. So if you plot this, no matter how much you zoom in on zero, the kink never goes away. And in fact, if you keep zooming, it just looks like the absolute value. No matter how close you get to zero, it still looks like the absolute value of the whole functions. And that kink never vanishes. It never smoothens out in the process of zooming in. Same with this Weierstrass function that we looked at earlier. If you zoom in at a point, like they did here, it still looks the same. You still get all these kinks. All right, so now so this is the intuition. So here's the point. The reason why I looked at the graph first rather than go through the calculations, because we want to develop some intuition for this problem. We want to know what's the reason, like what's the moral reason why it's not going to be differentiable at zero. And this is the reason, because if you consider tangent lines on the left or the right of zero, you're going to get different numbers. You're going to get -1 and 1. You're going to get positive slope on the right, but negative slope of tangent lines on the left. So now let's see the actual work and see how this works out. So keep that intuition in your back of your mind. So what we're going to do is we're going to compute the derivative. Let's see how well, they're kind of being, I don't like how they're doing this actually. So we're going to take x to be a little bit bigger than zero. So we're going to compute the derivative of a point to the right of zero. So if you take x to be positive, then absolute value of x is just going to be x. And then you can take h small enough, because remember, we want h to go to zero, so we can just take it small enough so that x plus h is positive. So h could be positive or negative, but whatever it is, it's small enough so that when you add x plus h, you're still positive. So again, h could be a negative number, but it's small enough so that when you add it to x, you're still a positive number. So then by definition, what's the derivative? What's this limit right here? And now because x is positive, this absolute value goes away. And because x plus h is positive, this absolute value goes away to give you this right here. And then when you simplify this, this x cancels with this, and then you get h divided by h is just going to be 1, so it's the limit of a constant. As h goes to 0, it's going to be the constant 1. So in other words, so that this is like considering the derivative of points to the right of 0, which is what we did when we looked at this graph over here. If you look at like a point here, I mean, the tangent line to this point is just going to coincide with this whole branch right here, and it's going to go right through a 0 like that. So that has a slope of 1, and that's exactly what this calculation shows. The slope of the tangent line to the right of 0 is 1. So what does this show you actually? It shows you that f is differentiable for any x positive. So it's going to be differentiable every positive number. And the same thing is going to be true for the negative numbers as well. So if so let's consider x is negative now. We're going to show that that f is differentiable even when x is negative. And what we're going to see in the process is that x is not differentiable at 0 though. So absolute value of x is equal to negative x. And again, we can choose h to be small enough so that x plus h is still negative. So so in this case, h could be a positive number, but we're going to choose it to be a small enough number because again, we're going to let h go to 0 anyways, so we can choose h to be as small as we wish. We're going to choose h to be a small enough number so that even if h is positive, x plus h is still negative. So that means when you take the absolute value of x plus h, it's going to be the negative of x plus h. So again, computing the limit, the derivative, we get this is the limit. This is by definition the limit of the derivative, and the absolute values go away to give you this. And when you simplify, you get negative x here, and then you have negative x, so positive x, so they cancel out. And then you have this negative distributes to this h to give you negative h in the numerator. And they have negative h over h is -1. So then the limit of this constant is just going to be the constant, which is -1. So when you are on the left of 0, the slope of those tangent lines is always -1. But now the question is, what about when x is 0? Well, you can kind of already see that it's not going to be differentiable at 0, because if you consider this limit from the left to the right, you're either going to get -1 in one case, or sorry, you're going to get 1 in one case when you're to the right of -0, but you're going to get -1 if you're to the left of 0. So let's see how that calculation works. So let's look at differentiability at x is 0. So by definition, it's going to be this limit right here. And when you plug things in, you're going to get this. And we're going to see that this can kind of flip-flop. This right here, this number here can be plus or -1. So we're going to do, to see that, we're going to compute left and right hand limits separately. So we're going to compute the limit of this fraction when h is approaching 0 from the right. And so we're considering, if h is to the right of 0, it means it's positive. So the absolute value of h just equals h. So h over h is 1. So limit is 1. On the other hand, when h is approaches 0 from the left, absolute value of h is going to be negative h. So then we have negative h divided by h gives you this -1, and the limit of a constant, just the constant, so -1. So if you approach on the right side, you get 1. If you approach on the left, you get -1. So because these limits are different, f prime of 0 can't exist. It just doesn't exist. So f prime. So what that means then is that the limit exists. That is, f is differentiable whenever x is not 0. For anything x, so whenever x is not 0, the derivative, or that is the limit, will exist. And then the formula for the derivative is given by this right here. So in other words, if you're to the right of 0, you have slope 1. If you're to the left of 0, you have slope -1. And again, you can see here that the fact with this, so this is just something we already saw. The fact that f prime of 0 does not exist is reflected geometrically in the fact that the curve does not have a tangent line at 0, right? There's no tangent line here. And that's kind of what we were hinting at when we first looked at this graph. Like if you try to look at, there's just no tangent line, because on the one hand, if you're really close to 0 on the left, you have a tangent line going this way, but if you're really close on the right to 0, you have a tangent line going this way. So there's no tangent line there. It has this corner. And then here is a plot of the derivative. All right, so here's a very important theorem that relates continuity and differentiability. So this says that if f is differentiable at a, then it's continuous at a. So in other words, um, in other words, what this implies is that every differentiable function, that is a function which has a derivative, so i.e. a function which has function which has a derivative, is continuous. So let me open OneNote. I want to prove this for you. So I put the book to the side. It's a really nice proof. And I think it's important to go through, because it's important to relate these very important concepts to each other. So it's going to turn out that differentiability implies continuity, but not the converse is not true. That is, continuity doesn't imply differentiability. And in fact, we already saw that with the absolute value, or even the Weierstrass function, right? The Weierstrass is continuous but not differentiable. So just because you're continuous, it does not imply that you're differentiable. So differentiability is a much stronger property than continuity. So this is a proof of theorem 4. So so what we want to, so we're going to assume f is differentiable at um x is equal to a. What does that mean? It means that f prime of a, which is this limit by definition, this limit, sorry, so it means that this limit exists. So this is what we're assuming. This is what we're starting with. So what we want to show, so want to show, oops, we want to show f is continuous at x equals a. And what does that mean? I.e., we want to show WTS just means want to show that the limit, oops, yeah, the limit as x goes to a of f of x is equal to f of a. So that's what it means to be continuous at this point, that you this limit exists and it equals f of a. So it's again, that's a strong requirement, but it's going to turn out that differentiability is even stronger requirement. So first, to get this, first we're going to show. All right, hold on. These dogs are barking. I probably can't hear them, but it's really distracting for me. So let me pause for a second. Okay, sorry about that. The dogs are barking a lot. So let me share. All right, so um, let me just start over. Just really recap. So we're starting with this. We're assuming that this limit exists. That's what it means to be differentiable. And this is what we want to show, that this limit exists and it equals f of a. So first we're going to show that, first we show that the limit as x goes to a of f of x minus f of a is equal to 0. That's actually really close to just proving this right here, and we'll see how. So first of all, um, note, we can say that f of x minus f of a is equal to f of x minus f of a divided by x minus a times x minus a, when x is not equal to a but near a. Let's say x is, so this thing is, I gotta really figure out why this computer's not working that well. It's ridiculous. Anyways, so x is not going to be equal to a, but it's going to, but but x is near a, and that's all we need for computing limits, is that x is not equal to a, but it's near a. So this equation holds when x is not equal to a, but near a. So now let's take limit. Let's take the limit of both sides. So we're gonna have the limit as x goes to f, sorry, as x goes to a of f of x minus f of a, and that's gonna be equal to the limit. So again, remember that was one of the rules we said, is that it said that if you have two functions which are equal near a point but not actually maybe at that point, then they have to have the same limits, right? I don't remember which limit law that was called, but there was like, if you have f of x equals f of g for x not equal to a, then you know that they have the same limit as x goes to a. So that's exactly the law we're using. So all these laws come up. Sometimes they come up in a like a subtle way, but we're always using these laws. And also now we're taking the limit of f of x minus f of a over x minus a, and that's gonna be times x minus a. Now the limit of this thing is that's the derivative by definition, and we know that it exists. And we know the limit of this exists also, so we can split these limits up, right? So we can just, or we can distribute the limit over the product times the limit as x goes to a, x minus a. And then, so as I said, this part right here is exists by assumption and equals f prime of a, right? Because we were assuming that the function is differentiable. So now this is the underlying part is just going to be f prime of a. Now what about this part though? Well, as x goes to a, x minus a should go to 0, right? So this is going to be 0. So the overall is going to be equal to 0. So hence, this limit up here equals 0. So let's write that down right here. As the limit is x goes to a of f of x minus f of a is equal to 0. Now, why does this help? Let's figure out, let's do this next step and we'll see how exactly it helps. So remember, what is it we're trying to show ultimately? Let's scroll back up. We're trying to show this right here. So let's start with computing this and let's add 0 in a clever way. We're going to add 0 and that's like a common trick in mathematics to add 0 in a clever way and multiply by 1 in a clever way. So we're going to take the limit as x goes to a of f of x. Well, I can just, inside this limit, I can add f of x, sorry, f of a, and then I can subtract it off, and I won't change the limit, right? So I added f of a, but then I subtracted it off here. So I didn't change the limit. Now, I can be, now this is a constant, right? So I can take the limit of it, and we just determined that the limit of this as x goes to a is 0, so I can split the limit up, right? So I can split the limit, distribute the limit in this way. And then I take the limit of f of a as x goes to a, so that's just a constant. And then I take the limit of f of x minus f of a as x goes to a. So this thing right here is just a constant, so it's going to be equal to f of a. But this thing we just proved is equal to 0, so this is plus 0. So it's overall just f of a. So hence, the limit as x goes to a of f of x is equal to f of a. And then that's just by definition means that f is continuous at x is equal to a. So then that finishes the proof there. So in sum, if you're differentiable at a point, then you have to be continuous at that point. But the converse is not false, is not true. That is, there are continuous functions which are not differentiable. So for example, the absolute value function is continuous at 0, but it's not differentiable. And the same thing with the Weierstrass function. So now we know a lot about differentiability, but what does it mean to be what does it mean to fail at to be differentiable? We saw a little bit of that, but turns out there are a couple ways this can happen. So for example, let me pull up the book now. So how can a function fail to be differentiable? Well, we saw that in general, if the graph of f has a corner or a kink, then the graph of f has no tangent line at this point, and so it can't be differentiable there. So in other words, and how you see that is if you compute this, if you try to compute the derivative and you look at the left and the right hand limits, you're going to see that they're different, and that's exactly what we saw with the absolute value function. If you take the right hand limit of if you try to compute the derivative of the absolute value function and you compute the right hand limit, you're going to get 1. Whereas if you compute the left hand limit, you're going to get -1. So these are the left and right hand limits are different, so that means the limit, the overall limit doesn't exist. So another way a function can fail to have a derivative is that if f is not even continuous at a, so it couldn't possibly be differentiable. And that's basically what we've just proved right here, right? So this statement right here is equivalent to the following. Equivalent. The following. If f is not continuous at x equals a, f prime is not differentiable there. At x equals a. And if you don't see that, it's more of so yeah. This is what we did was you take the contrapositive. So in other words, um, there's a more. I've probably used this rule a lot, and maybe you're not sure what I'm how these are two equivalent. But let me just write down something for you. So let P and Q be any propositions. For example, P could be the proposition F is differentiable at A, and then Q could be the proposition F is continuous at A. Then um, P, so then the statement P implies Q is equivalent to the statement not P, Q implies, and so not Q implies not P. This is called the contrapositive. These two statements are equivalent. So if you're differentiable at Q, at P, or sorry, if you're differentiable at A, then your continuous at A is equivalent to saying if F is not continuous at A, then F is not differentiable at A. So maybe that's obvious that those statements are the same, but I just want to point out that that's why they're the same, because it's based on this more general rule of right here. This is called the contrapositive statement. This is something you learn in logic. If you go in more advanced mathematics, you'll take a whole course on like basic first order logic, and this is something you'll learn. All right, so if you have a corner or a kink, you fail to be differentiable. If you're not continuous at a point, you fail to be differentiable. But there's this other option or alternative, this possibility is that you have a vertical tangent line when x equals a. So in other words, like you are so you can see from this graph, there's like this kink right here, this corner, which is kind of like the other cases. But in this case, this is different from the absolute value though, because these tangent lines, you can see that they're both approaching they're both approaching the vertical line, which has an infinite slope. In the case of the absolute value, you had the tangent lines approach completely different lines. Tangent lines were approaching the line with slope -1, the on the left side, and the tangent lines on the right side of 0 were approaching the tangent line with a slope of 1. But in this case, these tangent lines, they're both approaching a tangent line with an infinite slope. So this is a case where you don't exist, but it has to do basically again with this. I don't know why they're calling it a third possibility. It still has to do with this fact that you have this like corner or this cusp right here. So this, I'm sorry, this vertical tangent line nonsense arises when f is continuous at a, and this limit as you approach a is infinite, and that expresses the fact that your slopes of your tangent lines are getting bigger and bigger and bigger. They're approaching a vertical tangent line right here like this. Yeah, so this is just exactly what I said. This means when you take this limit, it means that the tangent lines become steeper and steeper and steeper as x approaches x approaches a. So here are the three possibilities. Basically, you have a corner or a cusp Um, here's a case, then you can have a discontinuity like we do here, and then here's a vertical tangent where you don't have a cusp. So you have like a vertical tangent at this point, but you don't have any cusp there. Okay, I see. I can now see how the corner case and the vertical tangent case could be different. I guess at this point right here, you'd have like the tangent lines are going this way and the tangent lines are going this way. So they're not approaching a vertical line. Yeah. Okay, I can see how those are distinct now. All right, so let's see. Yeah, this is exactly what he said earlier, but no matter how much you zoom in towards the point, like in figures 6 and 7a, you can't eliminate the sharp corner or the cusp. So here is differentiable at A. And remember, what does it mean to be differentiable at A? It means at this point, locally, as if you zoom in, starts to look like a straight line. So if you just keep zooming in more and more and more, you can't distinguish the graph of the function at this point from the tangent line at that point. They like coincide in a sense. They get very close to each other. But here, no matter how much you zoom in on this point, it's never gonna look like a straight line. You're gonna have this corner, this cusp. So it's not gonna be differentiable there. So that's another way of remember thinking about differentiability is roughly means that locally you look like a straight line. Locally, you look like this tangent line at that point. All right, so we've just been thinking about one derivative, but it turns out you can take as many derivatives as you want. So we have this notion of higher derivatives. So here's the first derivative, but the derivative itself may have a derivative of its own. Maybe you can take the derivative of it. And so when you want to take the second derivative, you just take the derivative. This means that to get the second derivative, which you use this double prime notation, you just take the derivative of the derivative. That's all that means. So f double prime is called the second derivative. Is called the second derivative of f because it's the derivative of the derivative. And then so that's using this one particular notation, but using the Leibniz notation. If you want to take you take the first derivative and then you want to take another derivative, this is the notation we use right here. D squared y over dx squared. It's just notation. These are not exponents in the usual sense. They're just to indicate that you're taking the second derivative of this function y is equal to x. That's all. And there's nothing to say that you can't generalize this. So you can even do dny over dxn. And this is just nth derivative. You take the derivative of m times of y is equal to f of x. The most we're going to do probably is just two derivatives. And the first derivative and the second derivative are going to tell you a lot about function. It turns out that the first derivative isn't enough. It doesn't give you enough information about the graph to like uniquely describe the graph. You also need the second derivative. That's going to tell you a lot of information, give you a lot of information as well. So I'm not going to bother going through this example. This is just more, this is just, we looked at this example already and we found, this is what we found the derivative to be. And then you can just go through the calculation to find the second derivative. So remember, it's the derivative of the derivative. So when you take the limit, you're not taking the limit of f, you're taking the limit of f prime. So you're using f prime. So I'll let you work through that on your own. And again, if you have questions, just let me know. I think that's it. Yeah, so that's all we have for today.